Okay, this is the example of a well-established CNN, which is called AlexNet. Actually, AlexNet is not the best well-established CNN that we have right now in the market, but this is the earliest one. I think the first one we can consider as the first one, because in some book they also mention this is second one, because there's another one which is the earliest one. There is one model, I forget the name, but it's the earlier CNN before AlexNet. Okay, but in some book they consider AlexNet as the first one which is implementing what we call a fully CNN. Okay, so that's why I think like I mentioned in the earlier lecture, that in your syllabus we only discuss about the AlexNet, even this is the earliest one, and again I'm not because this is the earliest CNN which is well established. Of course, the performance of this architecture is the lowest among the well-known CNN. Okay, because currently we have a lot of well established CNN which is better than AlexNet. Okay, you have a Google Nets, you have a VGG16, VGG19, you have a mobile net, and so on. Okay, which is the performance is better than AlexNet. But in your syllabus, let's just discuss one of it, because this, of course, we just want you to, okay, the objective of this courses, we just want you to have an exposure to CNN, or in exposure to deep learnings, and that's why we just introduce to you with this AlexNet. Okay, later if you want to apply other model, then you can just apply. Just the difference is just the architecture. It's still using the convolutional layer, subsampling layers, and with the fully connected layer. But just you have a different name because you have a different architecture proposed by many people, and once they apply their model to well-known data set, they find out their network become, the performance is 90% or should be above 80%. So that's why they create their names there. So I think for example, AlexNet might be AlexNet is come from people who you can search for it. Maybe AlexNet they use their name in the network, so that's why they call it AlexNet. And then because Google create the Google Nets, so they call it Google Nets. So might be one day you can have your own CNN architectures, then you can put your names there as one of the you can when you find out that your architecture, CNN architecture, can beat the existing well-known CNN, then you can have your own nets there, then you can get famous with it. Okay, so okay, activation function, I will not talk about this thing detailed, because we already talked about it in the previous chapter, artificial neural network. Okay, so again, activation function is attached with convolutional layer. So that's mean when we talk about convolutional layer, it's actually consists of two operations. One is a convolutional operation, and it end up with activation function to produce the activation map, or in other words, we call as a O matrix there. Okay, so again, this is the type of activation function that we have. Again, I already discussed this one. Is evolution. Is not, so which one is the best. Actually, it's not we don't talk about the best activation function, but we just talk about the evolution. We start with the linear activation function, and then come up with the sigmoid, and then because sigmoid range is 0, the range is from 0 to 1 only, then is not enough, or maybe the information is too little to be put from the range of from 0 to 1, and then they propose with Tan's activation function, because Tan activation function the range of output there is a little bit broader than sigmoid because it cover from -1 to +1. And but both of this activation function, the disadvantage is that we have discussed before, it suffer with what we call as a vanishing gradient, because when you update the when you want to do the back propagation by applying a sigmoid function, if you have more than one hidden layer, you will see that the update of the earlier W, which is close to the input, is very slow because the updater is very small. That is in that situation is known as a vanishing gradient. So that's why the sigmoid or TANS there is only popular for ANN. Okay, because the ANN we only have one hidden layer, so one hidden layer might not suffer with that. But if you increase the hidden layer more than one, and your network become deep neural network, then this one is suffer with your system will suffer with vanishing gradient, because the more hidden layer you have, or the more layer you have, then the updater of your W, especially that close to the input, is more and more smaller. So then the movement to update the W is very slow. Okay, and then so that's why in CNN or in deep neural network, they introduce to you with what we call as a ReLU. Okay, so because ReLU here, the purpose of showing introduced with the ReLU is because we want to avoid of that vanishing gradient, because now, because again I show in the website there, if you plot the derivative of sigmoid, it's something like this, the shape, because okay, it's very small. Same at this tan is something like this, very small. So it's very small, but this one, if you do the derivative of this function, this one become a straight line. So that's why the straight line is fixed. So that's why vanishing gradient will not happen here. So that is the purpose of why when you talk about deep learning or CNN, now the most popular activation or the most suitable activation function to be used for this one, for this CNN or deep neural network, is ReLU. Okay, and some of the researcher also introduced with some innovation, some innovation introduced to you to the community with what we call as a leaky ReLU, because they find out there's a disadvantage of ReLU is that you only entertain the input when you are at the positive side, but at the negative side you set with 0. So okay, so because they find out the disadvantage of ReLU is that on the negative side you set into 0, means that you are let's say the negative output actually is you just imagine in your neural network, if the negative you during the convolution you find out the output is negative, or during the matrix multiplication, if you talk about deep neural network, the output of that operation negative. If you apply the ReLU as activation function, then you are destroying that function, that output, because you don't consider negative as the information. So that's why from that maybe some people see that no, it might be some part of the negative output should be meaningful information of a good pattern. So if you apply the ReLU, then you will destroy that information or lost that information. So that's why they come out with the leaky ReLU. Okay, so that is the evolution of activation function. But because we talk about CNN or deep learning, so we only focus on this one. Okay, I will not we will not use this one again during our ANN class, we more to using this one. Okay, this is ANN, and then during CNN we will use this one, because now this one is the most common in convolutional neural network. Okay, because of this one is not suitable to be used for CNN. Okay, then you can just read that description there. I already discussed that. Okay, because of the gradients, and then vanishing gradient and so on. Okay, and then come out the ReLU. Okay, that's the points there. The ReLU unit can die because of this. You have a 0 here, it can be die. So how it can be die? Because it might be if most of the time the output of your convolutional operation is almost all output from the convolution operation is negative, then it will die. So that's why they put it as a leaky ReLU. But in our class we just focus on using this one.